Good morning, folks, and welcome back. While people are getting seated, let me take a couple of polls. How many of you got my two emails about this course? And how many didn't? Okay. Okay. So there were two emails that went out about preparations for this course. How many of you are actually here for the first time today? Weren't here yesterday? Okay. And by the way, how many of you have never used Mplus before? All right, so that's about 25%. And how many of you don't like to raise your hand? Now, I was going to say, on the Mplus homepage, you have a link here. For instance, there, in one of the margins, either one. And I just wanted to make you aware of the fact that here, if you look on the topic 3, you have introductory intermediate growth modeling that we talked about yesterday. And here's the old recording. The most recent handout is the one that you're looking at. And in a few weeks, as we revise this for the Barcelona presentation on the same topic at the end of May, there will be a new handout posted here, and that handout will have all the adjustments that we have thought about while we taught this. So for instance, you will get the input, a page with the input for the status change model for marital status and drinking. You will get a page where all of that input is given. So you can check that your notes are okay. So that will always be the latest, most updated, and probably we'll switch in and out some examples that we liked or didn't like and make some other adjustments. The most recent one will always be there. But of course, there's a handout that goes with exactly what was spoken here, just so you know about that. And another thing I want to make you aware of, here in the left margin, here. Here's where I go most of the time. So these are all the, if you're not aware of that already, these are all the papers that we have in PDF from analyses that have used Mplus, either ordered by topic or ordered by date, so you can look through them. So that's quite a big group of papers at this point. Just to familiarize you with the website a little bit. So let's get started with the second day. And it's a big day. It takes a while to get up. So we're going to take a look at the table of content here. Wake up. And it's a rich day. I hope you don't have to leave for your trains, planes, and automobiles too early, because it's going to go to the bitter end. 5 minutes to 5 we have to leave, at least. And we have to leave quietly, because there's a big event outside at the end of the day, a reception and some celebration of a new chairmanship, a special event here that they don't want to be disturbed. So we have a start here with advanced growth models, and we're going to move our way down through various versions on that theme, down to power computations for growth models, and then survival analysis, and at the end of the day, analysis with missing data that we're going to apply to these growth models, and try to see how we can most efficiently explore all of our data, drawing on knowledge that we have learned from survival analysis techniques and growth modeling techniques jointly. I just wanted to say a few words that I didn't say yesterday. the Mplus background has to do with the need, as we feel, and that we think we found a good response to that idea of integrating many good methods ideas from various disciplines, methodological disciplines, biostatistics, psychometrics, that are very much underutilized in practice and have been presented in a fragmented way. We've tried to integrate them in this one framework with one language that you can use in an easy fashion while still having very powerful and general modeling capabilities. And when I say we, that's not only Linda and I, but also our two full-time programmers, Thuy Nguyen does the interface programming, and Tihomer Asparojo, who does the statistical algorithmic programming. And then the Mplus office led by Michelle Kahn, and Gene Manager is there as well. So Thuy and Tihomer, they are very hardworking individuals, and who is my microphone going in and out, or is it? Am I okay? Is it going in and out? I'm okay, but the mic is not. So let me see. Am I stable now? Can you hear me now? Can you hear me now? All right. Sounds like it's working. So I was going to say that these two individuals, they got to have something to do because they're very energetic. So we have to give them tasks, and they are getting through them quickly, which is to say something happens with respect to the development of Mplus all the time. And it's not a static final product, but it's going to change very quickly over the months. So we'll have a new version within short, and after that, probably within 6 months, yet another little version, 6.1. So let me go forward and skip these pages and go straight to this topic, modeling with zeros, which we find on slide 16, an overview. And this is our way of orienting you where we are in this sequence of advantages of growth modeling in a latent variable framework. We've worked our way down these bullets, and we're now at the exciting spot of modeling of zeros. So now we're going to put together several of the building blocks that we talked about yesterday and that you master fully at this point. And we're going to talk about modeling with the preponderance of zeros, as it has been called in the literature. And we're going to make a distinction between two, we're going to focus on non-normal data. Non-normal data, and we're going to make a distinction between two cases, the one on the left and the one on the right. So on the left, we have 5 different categories. It could be a so-called Likert scale or Likert scale, scored from 0 to 4 or 1 through 5. And it looks a little non-normal. But on the right, we have the situation where it's not only non-normal, but you have a strong floor effect where you have, looks like more than 50% in the, at the lowest value. So it's like the full, we don't know whether or not all of these people are the same. If you change the question wording somewhat, we may have been able to spread them out. So it's like we have a floor effect here, and that's a very special variable that needs special attention. For variables on the left, like on the left here, you can actually treat those variables as continuous and apply an estimator like maximum likelihood. And although maximum likelihood assumes normality for continuous variables typically, the point estimates will be quite good even when the distributions look like that. But you do have to correct the standard errors and the chi-square for non-normality. If you have non-normal data like this and you ignore it, the regular standard errors are going to be too small. So you're going to have significant effects, more often significant disease tests than you should. So ignoring non-normality, using normal theory techniques, you have too small standard errors And then the opposite for chi-square, you have two large chi-squares. So you would reject a model that's not necessarily wrong, but just is a model for non-normal data. That's okay for this kind of distribution. I would use then MLM or MLR as the two estimators. But on the right, you have a situation that where already the point estimates would be off. The standard model, which are linear models for continuous variables, the standard linear models are not appropriate when data are of this kind. The assumptions are likely not to hold, and you will get biased point estimates. So that happens for continuous data, and very often happens for a special kind of outcome, namely a count outcome. So when the values are actually integer values, 0, 1, 2, 3, 4. How many times in the last 30 days did you do this or that, for instance? So it's a count variable, and there are special modeling techniques to take into account the high preponderance of zeros in that case. And you can also take a categorical variable approach, where this is an ordered polynomous or an ordinal variable. But sometimes you have so many different distinct values that you would, it's better to treat it as either a count variable or a continuous variable that is perhaps censored. Censored meaning that it cannot assume values less than 0 in this case. And so there's special censored normal modeling, and in regression analysis that's been called toe-bit regression. But that kind of modeling is available to us in Mplus for all kinds of situations, be it factor analysis or growth modeling. We're going to focus quite a lot on two-part modeling, or semi-continuous modeling, which there was an interesting article in JASA by Olson and Schaefer, JASA being Journal of the American Statistical Association, doing a longitudinal version of an earlier paper by Naihua Duan and others at the RAND Corporation in Santa Monica, where they dealt with data that looked like this, and they created a so-called two-part model for data of this kind, not focusing on counts, but a continuous variable that can assume values, not only the integer values, but has that preponderance of zeros. We also have a mixture model possibility here. For instance, if you work with counts, we have a very common mixture model that's called zero-inflated Poisson. And we're going to talk about that here this morning. It has a flavor of, part of that is a Poisson model, part is a logistic model, like we talked about at the end of yesterday. And there are other kinds of mixture models that we will talk about in August. Let's see. Let me show you these in terms of pictures here. Here's two-part modeling. Two-part modeling starts with a variable that looks like this. You know, that's kind of data that you don't want to show anybody that you have. They look much too skewed, and you can't even pretend that it is normal. But now you don't have to be ashamed anymore. These data can come out of the drawer, and you simply create two variables from this variable. One variable says, are you at 0 or are you not at 0? So here are the people who have 1, 2, 3, 4. That's one variable. It's a dichotomous or a binary variable. And for those who are in 1, 2, 3, and 4, you actually have a variable with those values as a continuous variable in this case. So a variable that doesn't have the value 0 but goes from 1, 2, 3, 4 and up. So you can think of this as if you take an NIAAA example, alcohol example, and we do that because we have been funded by NIAAA many times, many years. it could be frequency of heavy drinking in the last 30 days. So did you engage in heavy drinking or not? Not, and those who did. And if you did, how many times in the last 30 days did you engage in heavy drinking? Once, twice, 3, 4, etc. So that can then be represented as a parallel process growth model. So you have the binary part down here. So the U's in Mplus notation are categorical variables, in this case dichotomous, binary. And you have a growth model, say a linear growth model for that development, the development of the probabilities over time. And then for those who have engaged in heavy drinking, you have a growth model for the amount of heavy drinking over time. This could be years, for instance. And if you arrange your data like this, you can do a parallel process growth model, and Linda's going to talk about an example, talk about exactly how these variables are dealt with. Now, another model that we're going to learn about is the inflated growth model, and this happens then for count outcomes. And at this point, we're not going to even try to understand this diagram, but in essence, it is also so this could be a zip modeling, for instance, zip being zero inflated Poisson for count outcomes. But it also leads to a two-part model, but where one part is a latent binary variable, as I will explain shortly. An interesting situation that I don't think has been fully explored statistically yet, and it'd be fun to do that, is one where you have a lot of skewness like this, a lot of skewness in your data, a lot of strong floor effect, due to the fact that at a certain age, in a certain grade, for instance, a large proportion of your subjects have not yet started to engage in the activity. So like heavy drinking, for instance, in grade 8 or something like that. So you, at a certain point, then you're going to have a lot of people at 0, but then suddenly you come to a grade or an age where they start experimenting with that, and you have a growth model for the amount or for the frequency that they engage in that activity. So that then leads to what we're going to talk about this afternoon. You could have a survival model for onset of engaging in this activity. Time to onset of this activity. And once the onset has started, what's the growth curve for that? So it's a combined survival and growth model. And that I don't think we have mastered enough. You have the article here, Albert and Xi, but that's in biostatistics or biometrics, and it's for clustered data. I think it's mice, so it's not quite applicable. And there are special difficulties for behavioral data, because the definition of onset, although that's relatively straightforward when you're talking about tumor growth in mice, has a tumor started growing or not, it might be harder to define what onset is in behavioral studies. What constitutes starting to drink or starting to smoke? How much? What should define drinking regularly? You know, it's not clear cut what the limits or threshold should be. So onset in some way has a measurement error, which is an interesting modeling twist. Anyway, so this is a little bit of an overview and a look ahead to what we're going to talk about. Here you have two-part growth modeling, and I think that looks very applied and practical, so that must be Linda.
Probably.
Can't possibly be me.
Thank you. Okay, so now we're going to look at an example of two-part growth modeling, and we're going to be using the AMPS data, and these are data taken from the Alcohol Misuse Prevention Study, where there were 49 schools with approximately about 2,666 students who participated, and they were measured 7 times. What we're looking at, though, is just a small subset of the variables in that data set, and we're looking for 3 items related to alcohol misuse. The items are, during the past 12 months, how many times did you drink more than you planned to, feel sick to your stomach after drinking, get very drunk? And then we take the average of those 3 items is what we'll be looking at. And we'll be looking at 4 time points: fall grade 6, spring grade 6, spring grade 7, spring grade 8. And after yesterday, you should think non-equidistant time points. So that gives you your clue for your time scores there. So here's what the model looks like overall. We have 4 measurement occasions, the average drinking at time 1, 2, 3, and 4. And then we have the intercept growth factor, slope growth factor, so just similar to what we looked at yesterday. Now, this is the original variable. We're going to look at this as a 2-part model, so we're going to have to create the 2 variables from the original variable. So we show you here how this is done. And Mplus actually has a data 2-part function which will divide the variable into 2 variables for you. So if the original variable, which is called am_over, is greater than 0, then the binary variable, which we're going to call u, is going to take on the value 1, and the continuous variable, which we're going to call y, is going to be the log of am_over. If the original variable is 0, then u will be 0 and y will be missing. And if the original variable is missing, both variables, u and y, will be missing. We take the log. Olson and Schaefer recommend that. Mplus does that automatically for you in data 2-part, and also allows you to do no transformation or to do other transformations of that variable. So maybe we won't leave that there. Okay, so let's take a look at what the model that we're going to estimate looks like. It has the u part of the model down at the bottom and the y part of the model at the top. So y is continuous, u is binary. So it's like the parallel process model we looked at yesterday, but one part is binary, one part is continuous. We call the intercept growth factors IY for the continuous, IU for the binary, and the slope growth factors SY for the continuous and SU for the binary. And you can see that we're regressing all 4 of the growth factors on the variable, the covariate male, the time invariant covariate male. Okay, so we'll leave that there then. And as Bengt mentioned earlier, we have a lot of papers on the website that are available to you as PDF files, and there are a lot of applications of this 2-part growth modeling there that, if you're interested in looking at them. So here's what the input looks like. So what is new here? If you go down to data 2-part, this shows you that particular function, which you can use while you're just to divide the variables and save them for further analysis, or you can actually use it while you're doing the analysis. And one thing I didn't mention when I was looking at the pointing over here is that the 2 parts don't have to follow the same growth function, and they don't have to have the same covariates. So although we're showing just a single covariate for both, and the same covariate for both parts, you can have different covariates predicting the continuous part and the different ones for the binary part. And for example, the continuous part might be quadratic and the binary part could be linear. So there's a lot of flexibility. And you might want, as a first step, to actually look at the continuous and binary parts separately in order to find the best fitting growth model for each part. Okay. All right. So data two-part, the names option gives the names of the original variables. So m over 0 through m over 3. The binary option gives names that are going to be assigned to the binary part, and the continuous option gives names that are going to be assigned to the continuous part. And the names are statement in the variable command is only the names of the variables in the data set amp.dat. So the newly formed variables u0 through u3 and y0 through y3, they show up on the used variables list. It's, in a way, the data two-part is like the define command, and these new variables have to appear after any of the older original variables. So the used variables list, we have male first because it's an original variable. It's named in the name statement of the variable command. And then u0 through u3 and y0 through y3 have to come after any original variables because they're new variables. Then we also have to use the categorical option to say that u0 through u3 are categorical binary variables. So data two-part is convenient. It helps you, once again, not make a mistake in your logic in the define if you try to do it that way. So we're going to be using maximum likelihood estimation and numerical integration. The reason we need numerical integration is that when you have categorical outcomes and you have maximum likelihood and latent variables, then you're going to need one dimension of integration for each latent variable that involves categorical outcomes. Okay, so here's our model command. So we have a growth model for the binary part, IU and SU are the growth factors, and a growth factor for IY and SY, the continuous part. Remember the measurement occasions were not equidistant, so we reflect that in the time scores of 0, 0.5, because this was from fall to spring, and then spring to spring would be 1.5, and then spring to spring again would be 2.5. So the distance between the measurement occasions is reflected in the time scores. And we are specifying a linear growth model for both of the processes. So once again, 0, 0.5, 1.5, 2.5. And we're regressing all of the growth factors on male using the on statement. We're estimating, by default, all of the residual covariances would be free. So we're only, if we look at our path diagram, we can see that we're estimating the IY-SY residual covariance and the IU-SU residual covariance and IY and IU. So between the two intercept growth factors across processes and within process between the intercept and the slope growth factors. And because the default is to estimate all of them, we need to fix the ones we don't want to 0. And it's, you know, your decision which ones you want to estimate or not. So if you don't want them to be estimated, you say IU with SY at 0, SU with IY through SY at 0. So you can, any default in Mplus, if a parameter is fixed or free, the opposite can be done, providing that it doesn't make the model non-identified. Now, nothing new here except in the plot command. So we have two growth processes, and if in the plot command we want to plot both of those, you use the bar to separate the two growth processes. So series equals, we're saying U0 through U3, and in parentheses we say SU, so it takes the time scores for SU as the values on the x-axis, and then we say bar y0 through y3, and in parentheses sy, and it takes the time scores from sy for the values on the x-axis. So that's something that we didn't see yesterday, the plotting of two processes. Okay. So then we get our test of model fit, and because we're in this realm of categorical outcomes and maximum likelihood estimation, we don't get chi-square and the traditional fit statistics that you may be accustomed to, but we get a log likelihood value, and we also get AIC, BIC, and sample size adjusted BIC. Okay, so now here are our model results. So IU, SU, just to orient ourselves on male. So the binary part of the growth model comes first. And underneath that, we have the continuous part of the growth model. And if we look in the third column, we see that male has a significant relationship with the intercept growth factor for the binary part of the model, but not for the it does not have a significant relationship with the slope growth factor for the binary part of the model. And we see that same pattern for the continuous. So and what it's saying here is that males are more likely to drink, and then they're more likely to drink more. So this would be the interpretation of that. If you look down here at the IU with IY, let's see, the two intercept growth factors, for the intercept growth factor for the binary part and the intercept growth factor for the continuous part have a fairly high, a significant covariance. And this is possibly partly due to the fact that they come from the two parts of the variable come from one variable. So if you see that. Now I wanted to just remind ourselves of what we learned yesterday by recalling that the parameterization of the growth model for the binary part is going to be different from the parameterization for the continuous part. And we can see this by looking at the slide on the right here. We see that for the continuous part, the y variables, the intercepts are fixed at 0. And for that part, the y part, we have IY and SY being estimated, the mean, or the intercepts rather. But for the binary part, the thresholds are instead held equal, and only the slope intercept is estimated. The intercept, the binary intercept is fixed at 0, as we see here. So just to remind ourselves that we do use different parameterizations for the continuous versus the binary part. In this case with binary, had we instead let IU be free and fixed these thresholds to 0, the value 2.655 would show up where IU is. So the parameterizations are they're just different parameterizations. They don't change the results. And as I said yesterday, we do that for categorical and multiple indicator models because it puts less restrictions. Instead of fixing all the thresholds of an ordinal variable to 0, we can instead hold each threshold equal over time. And that's a less restrictive model. Now we have, oops. I'm going crazy. Okay, here we are. So here we have R squared. Now what's new here is that we have latent variables we're getting R squares for. So, and as you can see, they're not really large for the observed variables, but they're certainly larger than for the latent variables. And it is the case that it can be difficult, although we didn't try too hard with just one covariate male, but it can be difficult to find covariates that explain the variability in the growth factors. So that can be challenging. Now, you remember that we have a conditional model. So that means that we're not going to get means, variances, and covariances from that model for our growth factors. So as we mentioned yesterday, we want to use Tech 4 for that. So if you ask for Tech 4, then you're going to get your estimated means for the 4 growth factors and your estimated variances here on the diagonal and covariances. So when it's good to get into the habit when you're running an estimated model, or rather a conditional model, just ask for Tech 4, and then, if you want to go back and see what the model estimated means are for this conditional model, you can take a look at that. We get lots of questions about that. Why did my mean go negative, when I added a covariate to the model? So just remember that you're estimating with a conditional model an intercept, not a mean. Now, there's a paper here. It's called Beyond Multilevel Regression Modeling. It's by Bankton, Tiamir, Asperahov, and I think the date is... I don't see the date here, Bank. Do you have it? Oh, here. Nope. Oh, it's a chapter that's coming out, but it's on our website. Okay, so it's by Bankton Tiamir. It's new. It's on the website, Beyond Multilevel Regression Modeling. And what it did is, in this example, we have the same relationship between the covariates for both parts of the model, but it's certainly possible that that wouldn't happen. And what they did is they took a look at a model in the regular way. And they looked at the relationship. It was heavy drinking once again. And the result, if you just look at it as a one-part model, is that blacks drink less. But if you look at it as a two-part model, where you look at whether they drink at all, and if they drink, how much they drink, you see that... well, actually, I'm going to read it to you here, because I think they say it nicely in the paper. Consider as an example the covariate black. As is typically found, being black has a significant negative influence in the regular growth modeling, lowering the frequency of heavy drinking. So blacks drink less. In the two-part model, this covariate is insignificant for the continuous part and significant only for the binary part. This implies that holding other covariates constant, being black significantly lowers the risk of engaging in heavy drinking, but among blacks who are engaging in heavy drinking, there is no difference in the amount compared to other ethnic groups. So when you go to some of these models, you can get a lot more information out of your data. Your data can be allowed to tell you more. You can see more subtle relationships. So this is one of the reasons that we try to talk different models to you, so you use each one of them, but so you use one that may help you understand your data better. I think it's your turn.
And this is a model that seems to get popular among researchers. So I'll just add a little bit more on top of that, what Linda said. I should also mention that there's a paper on the website under the section of two-part modeling that concerns an intervention where the intervention has an impact on one of the two parts but not on the other. So you can get more nuanced intervention effects estimated. It's a paper by Brown and others, Eric Brown and others. Anyway, one key aspect here is that the two processes are correlated, not only by being influenced by the same covariate, but correlated, and they're quite strongly correlated. If you look at slide 33, you have a correlation between IU and IY on slide 33. That's 0.8. And that's also what Olsen and Schaefer found, which says that if your tendency, say that this is at the starting point, initial status, this is the tendency to engage in heavy drinking, that is, it influences the probability of engaging in heavy drinking. When that tendency to engage in heavy drinking is high, that person is also likely to drink a lot. So that makes sense from a substantive point of view. And those correlations can sometimes go up very close to 1. And we're not arguing that you should only correlate the intercepts. You can correlate all of them. We just try to keep the example simple. But the key correlations of the model, we would argue, are those three that are those three residual correlations that are shown there. Now we're going to go to the count situation. So this is an exciting area, which you probably have quite a lot of use for. It has to do with variables that take on only discrete values, starting with 0. How many times in the last month? It could be the heavy drinking frequency, for instance, or how many cigarettes did you smoke in the last week, or how many DSM-4 diagnostic criteria did you fulfill in the last 30 days, or something like that. So we then get to that beautiful French word Poisson regression, and you have this exciting formula which has, exclamation marks and e to the power of stuff. Good stuff, right? Yeah, and you don't always learn about that in your psychology intro stat, but it comes in after a while, and it's a very useful situation. We're going to talk about lambda here in a very simple fashion. Lambda is a key parameter. We should think of that as the mean. For simplicity now, it's the mean count. Lambda is the mean of the count. So if the mean is high, if the mean is low, then in this case 0.5, you're going to have a lot of piling up at 0. If the mean is very high, the distribution is going to move away from 0 and it's going to look almost normal. Now, in Poisson regression, when we always start with the regression building blocks, we formulate a model for Poisson as a function of x, x being, say, age, and the count may be a frequency of heavy drinking in the last month. As a linear model, this is a linear model, right? Linear model with an intercept and a slope for a dependent variable that is the log, e log, or natural log of lambda. So the log rate is a linear. A statistician likes to take log of things to make it easy to interpret, linear, but also whenever you take the log, it seems that statistical assumptions are more quickly fulfilled, like normality and the like. So that's really a useful model, but it's not useful enough. So immediately statisticians start tinkering with this. But, then you get these exciting words like zip. Do you do zip? Have you done zip yet? The problem with the Poisson is that it has a built-in assumption that the mean is equal to the variance of that outcome variable. And unfortunately, data aren't like that very often. Very often, data have variance greater than the mean because of this preponderance of zeros. True, this is a Poisson variable with rate 0.5. It has a preponderance of zeros. But the data would have even more of a preponderance of zeros most often. So then you will get into having to generalize Poisson to include zero inflation. And what zero inflation means, it's going to be now a precursor to your August course. It's going to be your first case of a mixture. First case of a categorical latent variable. So we're going to talk about two kinds of people. And let's have the heavy drinking situation. There are people who do not drink. So probability that a person is a non-drinker is pi. That's a probability. That's a probability of being in the so-called zero class, where you would only find u equals 0. So if you ask a non-drinker how many times he or she engaged in heavy drinking in the last 30 days, he's going to say, and she's going to say, 0. So you wouldn't say any other value than 0. But for those who are drinkers, their probability is 1 minus pi, and they add up to 1, because there are only two types of people. That's the probability of not being in the 0 class. And if you're not in the 0 class, we say you are a Poisson person. Your heavy drinking is Poisson distributed. No, it's all right. It's all right. I'm getting heckling here. This is just like the Senate. Anyway, so what's interesting then is if you observe a 0, you don't know what kind of person that is. It could be a person of two kinds. It could be a non-drinker, or it could be a drinker who happened not to engage in heavy drinking in the last 30 days because it wasn't over Christmas. So you have then a mixture at 0, and later on we're going to see mixtures, but we have to wait until August, mixtures above 0 as well. You have little mixtures, real heavy drinkers over there. But anyway, mixture at 0, so the probability of being at 0, of observing 0, is pi for the non-drinkers, 1 minus pi for the drinkers, and the drinkers follow a Poisson part, e to the minus lambda. For u equals 0, if you plug in r equals 0 in this case, then you're going to see that simplifies to e to the power of minus lambda. So that's the probability of observing a u equals 0 count. Now we also want to keep track of the zip mean count. That's important when we interpret our results later on. And the mean count with zip is not only lambda as it was in the regular Poisson, but it's lambda times 1 minus pi. And you also have the variance here. Now in zip, in regular Poisson we have one equation we're looking at in our model. In zip you have two equations. So you have the rate equation on bottom of slide 36, same as before, but now you have a logit pi equation. And since yesterday afternoon, you immediately know then that is a logistic regression. We just write it logit equals something, right? The logit of the probability, we know that that's the log odds, that's the log of pi divided by 1 minus pi. And if you assume a logistic regression function here for the probability of being a non-drinker, then that model becomes linear in X. So we're going to estimate the two gammas and the two betas here in our analysis. And we're going to be able to fit the data better because we do not force the mean and the variance to be the same. Now, you would think then that the statisticians were satisfied with that, but oh no, they have to go further and include the negative binomial, great terms, right? Very pedagogical, not. But it's an interesting idea. Negative binomial looks at the log rate again, top left, but it adds an epsilon, saying that the log rate for two people who have the same x value can still be different because they have different epsilon values. So even two people who are the same age, they don't engage in the same amount of heavy drinking. They differ by the epsilon amount which influences the rate. You don't see that epsilon in logistic regression or in regular Poisson regression. So it's an interesting idea. Who would have dared to bring in an epsilon there? You wouldn't think it was identified. But if you do that, and it is identified, then you avoid the tying up of the regular Poisson of the mean and the variance being the same lambda, and instead you get a new parameter in the negative binomial alpha, so that the mean and the variance are different. Now, if you want to know more about this negative binomial regression, we talked about it in topic 2, So it's on that video, but it is also a special Camtasia recording that I did at UCLA that's on our website, talking about the negative binomial when it was introduced in version 5 of Mplus, talking about marital affairs as one example, which is taken from a book by Hilby, a book devoted to the negative binomial, where you can explore the relative model fit of the Poisson, the zero-inflated Poisson, and the negative binomial. So when it comes to growth, now what we talked about so far is regression, not growth modeling. But regression is a building block in growth modeling. Then you have zero-inflated zip. We go back. We're going to stay with zip now. We're not going to do negative binomial growth modeling, but you can do that in Mplus. But we're going to do zero-inflated Poisson, which also avoids the restriction of the mean and the variance being the same. So we're going to work with a u variable, the count variable, and it count at a certain time point t for individual I. And again, it's 0, non-drinker, with probability pi, which changes over time, and it's Poisson with probability 1 minus pi. And then we're going to have the log rate model for a growth model where eta 0, 1, and 2 are the growth factors. So this is a quadratic growth model, right? That's a function of age. So that's the level 1 equation if you use multi-level terms. And here you have the 3 level 2 equations, writing out the random effects as they were, the growth factors. Here without any level 2 covariate, no time invariant covariate, in other words. So you just estimate the means of them and the variances of these z residuals, which may be correlated. And it may be good to note, it's described in the user's guide that you have on the website, but it's good to note that the probability of being in a 0 class is denoted as probability of the u number sign variable being 1, where u number sign is a binary latent inflation variable. So that's why I showed it as a circle before in that picture. So you can think of that, that's a variable that is categorical and latent at each time point, saying, are you a drinker or not, in this case? Are you a 0 class person or not? And with that, I think it's your turn.
Okay. So we're going to take a look at the Philadelphia crime data. I'll just leave that on both screens and look at a zero-inflated Poisson model. And we have a huge sample, over 13,000 of males, ages 4 to 26. And it's the count variable is how many times they had police contact. And we're looking at and individuals with more than 10 counts in any given year are deleted. And the data have been combined in 2-year intervals, and we're looking at starting at age 10. So the new thing here on the input is that we have a count option. And like the categorical option, it identifies the variables that are count variables. So any variable that is you want to be treated as a count variable in the model estimation, you would put on the count list. So we have Y10 through Y24. So we're looking at ages 10 through 24. And the I in, if we didn't have an I in parentheses, we would just do a regular Poisson model. But because we have the I in parentheses, we're going to be estimating a zero-inflated Poisson model. And we have a lot of other models that we can estimate for these variables. I don't think you said that, did you? So negative binomial inflated, negative binomial hurdle. There's all kinds of them, and they're in the version 5.1 language appendix, which is on the website with the user's guide, if you're interested in those. So here we're, once again, here's our growth model. In the analysis command, you'll see we have process equals 4. That's if you have multiple processors in your computer. And interactive equals control.dat. That allows you to watch what's happening in your analysis on the screen and stop the analysis and make a change. So you can read about that in the user's guide if you're interested. But the important thing is we're going to be estimating a quadratic model, and the measurement occasions were equidistant. So our time scores are going to be 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and 0.7. And the reason that we're using smaller time scores is because we have the quadratic part of the model, and the time scores for the quadratic part of the model are the squared linear time scores. So if we had 7 instead of 0.7, it would be 49, and that's getting to be rather large for a time score. So we estimate the model, and once again, we don't get chi-square related fit statistics. And then we take a look at the results. Now, the means of the growth factors are in a log rate scale. And if you exponentiate those values, they become the mean of the count variable. So when you look at them, you have to remember that for interpretation purposes, that you don't want to just assume they're like on the same scale as they would be if the outcome was continuous. So they're on the log rate scale, and exponentiate them to get the mean count. Now here you see what Bengt referred to as the zero, for the zero class. I didn't mention that when we were talking about the language. So when you have an inflated part of the model, you have not only the y variable, but the inflated part, which is referred to as y number sign 1. And so we have y number, we have the y10 number sign 1, 12, 14, 16, 18, 20, 22, and 24. Like I said, the data's in 10-year intervals. So these are logits. The parameter estimates are logits. And they can be converted to probabilities. And if you have a positive logit, like we have here, then the probability, there's a greater than 0.5 probability of being in the zero class, and a negative logit, less than 0.5 probability. So there's a greater than 0.5 probability here, and we could estimate what that exact probability is at age 10. And then you can see that it becomes more likely that you're going to be in this class over time as age increases. Or less likely, less likely. So the older you get, the less likely you are to be in the zero class when zero is crime or police contacts. So as you get older, you're more likely to have more police contacts. And you can see here all the intercepts for the y part are fixed at 0 as part of the growth model parameterization. And then we have the variances of our intercept, slope, and quadratic growth factors. And the covariances among the growth factors. So for example, S with I is negatively correlated. We see Q with S negatively. So here we have those covariances that you can look at. Now, on the next picture is a plot over years 10 through 24 of the mean count. So that's the exponentiated values. If you look back on slide, whoops. let me put it up over here, 43. So these values are up here. Oh, now I'm confused, Bengt. I think you need to help me.
Yeah, no, you're right.
Am I right? Okay, so it's the exponentiated values over here.
No, up there. So Linda was saying that you have to exponentiate these values to get to the mean. So for instance, if you look at the starting point here, if you center at the first time point, which is age 0.
Oh, right. Okay.
Then the mean of the count is influenced by the intercept factor only. If you take e to the power of minus 4 point something, you get a very small positive value, which is the one sitting down here. And then for later time points, the s and q means will also come into the picture, and you will have to compute the mean, but at the end, you take the e to the power of to get this curve. So it's the mean count, not the log mean count.
Right. So anyway, so what you can see here, the mean count of police contacts, the average count over time, and you can see that it peaks at age 16. So there's an increase in police contacts up to 16, at which point there is a accelerated decrease and then deceleration after that till age 24 and probably beyond, if you went beyond. And then we can also take a look at Tech 10 for this data. Besides providing the response patterns for categorical variables, we also do it for the count variables. So you can see here, these over time, this is somebody who had 0 counts throughout. And here we have somebody who has 0, 0, 0, 1, and then the rest zeros. And down here, somebody who had 2. So a count of 2 and then all zeros. So you won't see in the response patterns just zeros and ones the way you did for categorical. Have 2s. And if you look at this, you'll see that for somebody who didn't have any crimes at all, in the observed number in the data is 8,021, while the estimated is 7,850. So you can see that, you know, we've underestimated here. You can see that's significant. And for the response pattern 0001, and that would be 10, 12, 14, 16. So somebody who had a police contact at 16 only, which is the peak in the picture that we saw, we're going to overestimate. So we only observed 572, but the model's going to estimate 673. So, and then, you know, you can look at all the different response patterns and see where you find model misfit. Because like we said, we don't have fit statistics when we go into the realm of count variables and categorical with maximum likelihood and random effect models with, except for growth models. But we can use Tech 10. It's very useful, and I think it's fairly underutilized from my experience, because I guess people don't know about it, and I'm not sure how, other than when we teach, we can tell them about it. You can have a flasher on the homepage saying, use Tech 10, see user's guide or something. But anyway, it really is useful. I mean, if you really, really want to know where your data don't fit, I think it gets way closer to giving you information than a single fit statistic like a chi-square. It lets you really see where the model misfit may be. And then I think that's all. Can you get up?
Didn't we So let's just take 2 minutes to prepare for the after coffee break activity. And it's about multiple populations. And we talked a lot about that in topic 1 afternoon in the confirmatory factor analysis and structural equation modeling setting. And it's quite a lot of intriguing modeling possibilities there. It's a big topic. We won't have time to redo that topic 1 afternoon. So if some of this seems heavy for you, you can go back to those slides and that video. I should say that's sort of a general comment. If for some of you, some of these topics are brand new, know that you can go back to these videos. Know that there are many courses out there taught by others that give the introductory material. That's true for SEM. That's true for multi-level modeling. So you have those basic building blocks very clear to you. We're sort of trying to do that, but take off from that and show all the things beyond that you can do. But when we try to go beyond, it can be a little frustrating for those of you who are beginners. But you'll get there. So this is going down our list again to see where we are in the table of contents, so to speak. We talked about modeling of zeros. Now you know what it is. And we are now turning towards the rest of the day here. Multiple populations is the next topic. And we're going to make a distinction between 3 cases. And one is a simple approach where when we talk about multiple populations, we sometimes say multiple group analysis. So take as an example that it is an analysis where we're interested in gender differences. So it's a joint analysis of males and females, and we want to explore which parameters are the same for the 2 groups and which parameters are different. And we could have, for instance, the group membership, group being male or female, yes, as a dummy variable, as a dummy x variable, 0, 1, as we have had so far. That's one possibility. So we have a covariate. The group variable is a covariate. That gives us some analysis possibilities. But we can also do a so-called joint simultaneous analysis of the 2 groups. That's what we call the multiple group analysis. And that has some advantages and some disadvantages over the first approach. And we're going to also talk about multiple group analysis for randomized interventions, because that's a particularly rich setting which has intriguing modeling alternatives in it that are come about because of the specific design that we use in the randomized intervention. But since we are at slide 50, which is perfect since the total number of slides is 200. 200 divided by 4 is 50. And we have 4 blocks, and it's 9:45. I will stop right there and let you ask questions. So let's see who has energy here the morning of the second day. Yes, this lady.
Can you go please to slide 28?
28.
Slide 28.
Do you mind just going through the interpretations? If, let's say, each of these indicators was estimate.
So the question is about slide 28, the 2-part model and the interpretation of these estimates say that they were all significant. How would you interpret them?
One at a time, please.
One at a time, and slowly. Do we want to do that, really?
Go through each one?
Yeah.
Well, there
First 4.
there are only 4.
Well, you have...
You can't trick us. No, really. But, no, I think that's... Well, okay, they're all IU, SU, IY, and SY are continuous latent variables. So they're all linear regression coefficients. And
Wasn't that good? That makes it easy, right?
And male is binary.
Yeah,
So okay.
So at this point, since the dependent variable is continuous, albeit latent, we have linear regression. So it's a standard way of reasoning. As x increases 1 unit, beta tells you how much y increases. And in this case, x is, so for instance, we only have a binary x. Compared to females, males have 0.569 higher value, expected to have that much higher value on the IU. Now, the IU may seem a little artificial to you at this point, but just think that that's an initial status, which is the initial status value that influences the probability of engaging in the activity.
I'm sorry, you don't need to say the numbers. I'm just wondering about the concept.
I'll skip the numbers.
Right now the interpretation was that males males drink more, and then they have tendency to drink more.
Yeah, so here you have the tendency. This is the male have a higher tendency to drink.
So that's the binary part of the model.
That's the binary part. Higher tendency to drink, to do heavy drinking.
And the continuous part of the variable is that their males drink more.
Here, males have a higher, are expected to have a higher amount of drinking.
So the variable, that am-over variable, it gets divided into two parts. The 0-1 part, do you drink or don't you drink? And then the other part, which is how much you drink. So, that's why the IU is that they're more likely to drink, and the IY is that they drink more.
Now, if slopes were positive, were significant.
So now, the SU, okay.
If that was greater than
Significant.
1.96, yeah.
Let's see, SU.
Then SU is the slope in the development of probability of drinking heavily. And it says that males have a lower slope than females. So we have to, if you imagine that the slope is positive, then males have a less positive growth than females. Well, all we need to say here, all it says at this point is that males have a lower slope in their development of probability of heavy drinking than females.
So that's growth in whether they drink or not. And then the other part, the SY, is how the development, not development really, but the development of how much they drink. So we have two growth curves, one that looks at whether they drink or not, and one that looks at how much. Does that help, I hope?
Okay, that's a start.
Okay, well, think about it. Then we'll ask more.
Please. I'm wondering how you might combine what you talked about yesterday with the simultaneous growth processes with this two-part model. So in other words, if you have two variables that have the same zero category. So for example, if in addition to looking at heavy drinking, you also wanted to look at number of days per week that's
Right. So you're just asking the difference, or to contrast parallel processes and the two-part.
I'm actually asking if there's...
You want to go from 2 processes to 4, it sounds like.
Well, that's what I'm wondering. If they have, so if the two variables have the same zero category.
Oh, I see. So, okay, so I think, let me repeat the question, at
Right.
least how I interpret it. Can make of it what I want, right? So
She
the
won't
question
agree.
is, you have 2 processes going forward, which would mean that instead of parallel processes, it would be 4 processes. But this individual suggests that this
see.
part is
Two
in
parts.
common to the 2 processes. Well, there's a paper for you to write. I haven't seen that. So she's going for it. So what is the application, and why would they share the 0 part?
Well, I'm thinking specifically in terms of my research. I look at development of risky sexual behavior.
Mm-hmm.
So I'm thinking that there are a number of variables that I look at for which it matters that there are a lot of people who are not sexually active. So, for example,
At a certain time point.
at a certain time point. So, for example,
But if they are, there are lots of things that you could study about them.
yes, exactly.
continuous things. Yeah, I think it would be true. So it would be 1, 2, 3 processes instead of 4.
So you're saying that you like have two variables, and on those two variables, the people who have zeros are the same people?
Yes.
Okay. Yeah, no, that would make sense. And then, I mean, if that's really it, then you would have one zero part and several non-zero parts.
So in order to add, would I just add would I break one of the variables into two parts and then add the...
Yeah, so then you would have y1 would be a process of greater than 0 for one variable, y2 could be a process of greater than 0 for the other variable, y3 could be... does that make sense, Bengt?
Yeah, so you couldn't do this automatically by data twopart in Mplus, but you could create it yourself. But you have to remember that when you create the y variable yourself, you have to have missing for the y when u is equal to 0. So you have to do that correctly.
So define the
Yeah.
y variable with missing values at the 0 point.
Yes,
But if you
that's
look
right.
at-
You can use data twopart for
Yeah.
one of the two models, and then you use define for the second y variable.
And the
so
rules-
which journal are you going to send that to?
The rules for creating the variables are in the user's guide under data twopart. So.
More questions? Yeah, another paper? Yes. Say that again, please.
I can't. So what's the
I thought it
question?
was to sip or not to sip. Talking. Where is it? 36. 36 and 37. Yeah, so the question was, how different does the mean have to be from the variance for us to switch over to zip? Well, I would, you can watch that web video Camtasia recording from UCLA, but I would just go by BIC. Look at the log likelihood and the number of parameters and see which model has the best BIC. I would not look at the data. Well, sorry, I shouldn't say that. I would look at the data, of course, but I wouldn't let the data decide if the mean is equal to the variance as much as I would just test the two models against each other and see which one has the best BIC. That's a very pragmatic approach.
And under what circumstances do you move from zip to a zero negative binomial?
Under which circumstance do you use a zip versus a negative binomial? Yeah, so that's true. Usually the negative binomial is a replacement for a zip, but you can also have a zero-inflated negative binomial, although I don't know how often it's needed. And then you can have hurdle negative binomial as well, which is hurdle meaning two-part. Well, that's what it says here at the bottom, at least. But under what circumstance? Well, either you could go by BIC again, or you can reason substantively if you're particularly interested in the zip idea of a zero class, if that's relevant for your substantive application. Then you may want to go that way, because the negative binomial has no zero class. Clearly, the inflated negative binomial has a zero class, but the negative binomial does not. It seems like the negative binomial seems to be, if I can interpret the mood of the statisticians, seem to be a little bit preferred over the zip by statisticians, but I couldn't really say. I would let say BIC decide. The lowest BIC wins. Yes, Michael.
It's actually sort of a follow-up, and then I have a second question. It's an idea that Linda had given me when I asked a similar question to this woman, was that I think you can do an unstructured model. You can allow for the inflation using that count parenthesis I, then not structured in terms of the growth and look for whether any of the inflation estimates are different from zero. I found that useful in my own decisions about should I zero inflate or not. I don't know.
Mm-hmm.
That's just a comment. And then the question
23?
Let me just make a comment on that regarding the zero inflation. If you look at slide 19 before we go to 43,
Is it 43 or 23?
to play on your comment that the zero inflation here can be structured as a growth model or not. You can have a parameter for the mean of these, so before means, or you can have a growth model, in which case there would be only two means for them. So how to work with the inflation part is also an open question where you can have more or less flexibility. As you were saying, it sounds like you would take first step estimating this model and get the four inflation means and see whether it was the inflation part was needed or not at a certain time point. Okay, back to slide 43. Yeah. Yeah, that's right. So the question is about substantive meaning of plus versus negative signs. I don't think so. So you exponentiate it. A negative sign means it's very close to zero. If it's positive, it's much greater than zero. But then you also have to factor in the inflation parts here. You know, the mean is not only a function of lambda, but also of the inflation pi at a certain time point. So I don't look at these numbers very much. This number I certainly don't look at. I look at the plot that Mplus produces. I look at the significance of S and Q and the regressions on other variables, but the I I'm often very uninterested in, at least the mean. I am interested in variance of I to know if there's heterogeneity at age 10 or not. Okay. Yes, gentleman in the third row.
Yeah, so you talked to us about zip models can be used when there's a preponderance of zeros in the data. Can we still use a model like this when there are lots of values at the upper end of the distribution? So instead of zeros, a lot of values at the upper end. Or what kind of model is that called?
So when you say a lot of values, do you mean that they're not integer anymore, but they are 1.5 and 21.6?
They can still be integers.
Okay.
So
So like
ceiling
a
effect.
lot of values at 4, right?
So the opposite of that picture.
So-
Just flip that.
So you have this feature, but then it goes up again at 4. And that's what I alluded to as a mixture above 0. So that's what we'll talk about in topic 1, 2, 3, 4, 5 in August. So that's saying that there's some people who don't engage in that activity very much, and then you have another set of people who are very much into that activity, and their mean hovers around 4. So there are two classes of people, three classes. There's 0 people, the people close to 0, and the people who are very far from 0. So that would be a 3-class model instead of a 2-class. So that's a mixture zip, or a zero-inflated Poisson mixture model. So you can do that, yes. Yes, front row.
Yes, I have a question on slide 32.
Slide 32.
And the question is, how do you interpret those meanings if you do? I mean, they, for example, the IU and the IY, very similar in size. Are these on, what scale are these on? Are these interpretable? How would you...
So the question is about interpreting the means of IU and SU. And yeah, IY and SY, they're interpreted in line with yesterday. IY has to do with the mean at time point 1, or where we center. So that just has to do with the scale that you're working with. It could be 50 in L, say, and here is 0.3 because it's a different scale. So IY is usually very uninteresting. SY is interesting, meaning that it's positive growth. You have to know there's 0.2 units. You have to know what the scale is then of the outcome variable, but it tells you more directly about the slope. Now these values here are less directly interpretable. We want to know that that's positive. That's true. But since it is a change in the log rate, it's hard to interpret. It's sort of, you have to plot it to get at it. And IU, it's the mean of the log rate at time 0 at the initial status, but it doesn't have to do with a count because you have, what do we have? Do we have 0 intercepts for count?
I don't know.
Yes. Well,
Okay.
but it has, you have to mix that together with the inflation probability, lambda times 1 minus pi again. So I find that these don't tell me very much, except that that's positive. I sort of have to plot
I
them.
think we do have I at 0 for count.
Yeah, okay. So there's not an intercept parameter. Yes.
The Philadelphia crime data example with the zero inflated Poisson. In the input statement on line 40.
Which slide?
Slide 40.
Oh, okay. Sorry, I didn't hear.
The inflated part comes about because of the Brackenham bracket. That's what you said on the count one, right?
The zero inflation comes about because of I in
Exactly.
parentheses here, yeah.
So that gives you a threshold, or it gives you a binary probability at each of the time points in the output. But could you do that as a growth? Could you model the zero inflated part as a growth too, the binomial?
Well, that,
Yes. Yes, you could.
Have I got that right?
Yeah. So it's a very good question. The question is, and this is high-level stuff, so don't feel bad if you didn't catch it right away. So the question was, actually, we could have a picture 33 on the other one.
33?
I think so, or something like that.
Is that it? No.
Let's see.
Whoops.
There. If you look at
Right.
these two, this is exactly the choice. What do you do with the inflation part? And Michael would, he would do it this way. He would let each time point have its own unstructured inflation probability, where at 24 you hardly need it. When it goes down to minus 15, that implies you don't need it. This says a low negative value close to 15 says you don't need a zero class. These kids commit crimes at this age. But you have these different parameters, all of these different parameters. But on the right, it's suggested that instead of having all of those different parameters, this is the inflation part, the latent binary variable that says, are you in the zero class or not at time 1? Are you in the zero class or not at time 2? It can be structured as a growth model. So instead of, in this case, 4 parameters, you would have 2 mean parameters. And it's a very interesting type of model. I'm glad you asked. Because it is a parallel process model with a continuous part and a binary part, except that the binary part is latent. The dependent variable in this growth process is latent. And you can then feel your ground shifting under your feet, right? And so it could be simplified. Depends on the application whether or not that simplification on the right is good. It's more parsimonious, certainly, but is it good enough? One more question before you get coffee.
Okay.
Yes. Slide 46.
Oops, I did it wrong.
I'm sorry, I can't hear you. How you get this point? I asked Mplus to plot it. No, but it is the same. You have a growth model. It is from slide 43, I believe. Yeah, let's see.
I'll do 43.
It is using these estimates.
But I think you have a formula in the earlier.
Right. It is these estimates and the inflation. So you do the usual calculation. the mean at the second time point is I, the mean of I, plus the time score, which is 0.1 times the mean of S, 0.1 squared times the mean of Q. But then you also have to bring in the inflation probability for time point 2. So it's using those three values plus that value to get you to this. So it'll be a little bit harder to do on your cell phone, but it could be done.
Well, I guess
And with that,
then we should take a break until 10:20.
10:20.
15 minutes.
As we said when we started this round of 8 topics, this is going to be our last tour. That is, we've done the 8 topics a year from today, and then we feel we've said what we had in mind about those 8 topics. So the series is not going to continue unless there be a second last tour. But our intention is that we have then the material on the videos, and we have tried to train people like yourself who can give courses. And there are many others in this country and other countries that give courses on Mplus latent variable modeling. And we will come back and give courses on new topics as exemplified by the August course. However, there is also another vehicle to save the day, and that is the fact that we are writing a series of books drawing on these topics. And the first book is coming out early fall, and it's going to be a very applied book, but it's a book that has time to go into the details of the methodology and the examples, all the things that we have to sometimes sprint past is going to be in those books. And I don't quite know how many books there are, but it looks like there's a lot of them that can be written. When you start expanding on what you said in one day, that's a book in itself. So you can imagine. But we want to provide that service so it will be in that fashion, a summary of what we have taught during these courses. So we hope that's going to be helpful to you. So now everybody seems to be seated, and we're getting back to slide 50 and the 3 ways of analyzing multiple groups or multiple populations. And I am doing these slides, right? So let's take a look at the first approach, where the group variable is a covariate. And let's take an example that I know interests many. And that's an example where you have a treatment control dummy variable. We call it Tx. So it's a dichotomous or a binary variable, x variable. And we have 5 time points. And right away, we're going to jazz it up by saying that we have an intervention that happens here. You may want to draw a line here. The intervention happens after y1. The intervention happens after y1. So y1 is often characterized as a baseline value. A baseline value. We're going to play on that theme more today, this afternoon. This implies that if you have a treatment control dummy variable, that it should not influence eta 0 when eta 0 is defined as initial status, which it is in this case because the time score for eta 1, for time point 1, is 0, as is indicated by the absence of an arrow here. We have centered at the first time point. The time score x sub 1 is 0, which implies that this eta 0 is initial status, the pre-treatment systematic part of the variation in the baseline. And therefore, due to randomization, Tx should not have a significant effect on this variable. And that was what we saw yesterday afternoon in the schizophrenia example, the placebo drug example that came out to be insignificant. This effect came out to be insignificant, validating that the randomization was not only done, but actually was designed, but not only designed, but also worked out in practice. But what we're looking at is the treatment effect on the slope. So here we move away from the ANCOVA type of thinking, where the treatment effect is on an outcome at a certain time point, like pre-test, post-test. The treatment affects the post-test, and we control for the pre-test. This would be the pre-test here. Now we have a much more intriguing view of treatment effect. The treatment effect is on the development. The slope here has a different mean for the control group than the treatment group, is what this arrow says. And that implies that the development from Y2 to Y5 is going to differ between treatment and control group. So it's a much richer framework for assessing treatment effects. And we're going to talk about that situation more in detail further on. The alternative approach to dealing with several groups simultaneously is the so-called multiple group approach or two-group approach. So here we could look at it as this is the control group development, and at the bottom you have the treatment group development. And I write them underneath each other to sort of indicate that you can think of it as a data matrix. First come the control group people, then come the treatment group people. But the variables, the columns in the data, are the same. It's the same 5 time points. And this is then can draw on CFA SEM thinking in the multiple group setting that we talked about in topic 1. And that would be, it's a long story, and then that's going to go through some aspects of that story in the growth setting. But essentially, we want to study which parameters are the same and which are different in these two groups. So we could do the treatment control group analysis this way to see, for instance, if the slope mean is different in these two groups. We're going to take another approach, however, that is a little bit better, another two-group approach that's a little bit better for randomized intervention studies. I couldn't help myself at this point. I needed a formula page. So you have it here, but let's not get into the formulas now. Instead, let's look at the bottom on slide 53, the analysis steps. Separate growth analysis for each group is recommended in multiple group settings. Joint analysis of all groups, where the structural parameters, such as the growth factor parameters, are different. And then the analysis where we hold them equal to test if they are the same or not. For instance, testing that the slope growth factor mean is the same or different for treatment and control. Here's a very special application of multiple group analysis that is quite useful. It concerns the multiple cohort situation. And it is also called an accelerated cohort, and here you have it in different colors. So the way to read this is that the x-axis, so to speak, is age. And we like to keep age as the x-axis because typically that would be the time axis that we do growth modeling with respect to. So ages goes from 18 to 36. This is the NLSY, National Longitudinal Survey of Youth, I believe it is, for which NIAAA, the Alcohol Institute, had a supplement to measure alcohol use-related questions during the years that are marked in the squares, in the cells. So 82 refers to 1982, up to 1994, where the study was tragically ended. I think that was a pity. And what we're looking at here is different birth year cohorts. those born in 1957 down to those born in 1964. So 8 different birth year cohorts, which you can think of as 8 different groups of individuals in the multiple group sense. So 8 different groups. Now you could rearrange the data. You often see the data arranged with measurement year as the x-axis instead. But it's advantageous, we feel, to portray the data in this way. So if you look at it then, for instance, for individuals who are age 22, we have, so at the time point, so you have, these are the time points. So at the time point, age 22, we have measures, we have data from 1982 for those who were born in 60, but those who, in 1983, those who were born in 61, they're also 22. So we have 1, 2, 3, 4 cohorts contributing to the information about development at age 22. At age 18, we only have 1 cohort. Likewise, at age 37, we have only 1. So the idea here is that you can do a multiple cohort analysis that covers a very wide age range in a relatively short time period. You know, so the difference between 37 and 18, that's a much larger age span than the difference between 94 and 82. So the study can be completed faster if you do these multiple cohorts, staggering them with respect to the birth year. That's what's the acceleration is, that you can complete your study before you retire, basically. So here you could have the basic assumption that all these cohorts, all these 8 groups, have exactly the same parameters. They follow, say, the same growth model for whatever outcome you have that you study growth of over 18 to 37. Or you could test that invariance assumption to see where potential differences between birth year cohorts lie, where those differences lie. And you can do that in a multiple group analysis very effectively. And actually in the user's guide, we worked through a hypothetical example of this kind in detail, so you can see how data is arranged and how the model is set up. But we have an example of this coming up shortly. There are actually 3 different approaches that you can take to cohort structures. I was talking about this. I was talking about this analysis. And it is a multiple group analysis. I say using 7 Ys. I don't know if it's 7. It's actually 1, 2. The white squares are where measurement took place. 1, 2, 3, 4, 5, 6. Yeah, there are 7. So there's 7. 7 Ys for each of the 8 cohorts. There are 7 Ys, and we just fix the S at the time scores corresponding to age or age transformed. Instead of saying 18, you may want to say 0. Instead of saying 19, you may want to say 0.1. But that's a multiple group approach. You should also be aware that there are single group approaches to this, where you can look at the data as variables y18 to y37. So many more than 7 variables. You look at this whole data sets, all of those variables up here, where each group has missing data. All of these filled or shaded squares correspond to missing data. So every one in the sample has missing data, planned missing data, where you use, so you designate the missing data here. That analysis can get heavy. Single group analysis using all of the variables can get heavy, quite heavier than the multiple group analysis, because you have such low coverage. Coverage referring to what, as we will talk about later today, what proportion of the sample has has data on a specific variable, and pairs of variables. So the coverage can get low in this case, and that can make it complicated. Not so complicated estimating the growth model, but which is the H0 model, but can get complicated estimating the unrestricted H1 model, because the unrestricted H1 model estimates covariances between, say, Y18 and Y37, and there's nobody who has data on both 18 and 37, right? Certainly not the first cohort. They only have 37. Not the last cohort. They have data for only 18. And so that's that alternative. And then lastly, the single group approach using 7 Ys and the ACT option with t-scores, individually varying times of observation to capture varying ages is a possibility as well. I'm not going to talk about that now, though. So that means it's time for Linda.
Whoops. Is that the right slide? Yeah. Okay, so we're going to talk about the multiple group approach. The third one that Bengt mentioned or had on that slide. And we're going to make it simple. Look at 2 groups so that it'll make it easier to understand how this works. And like Bengt said, we have, for the first approach, which is just stringing the data out and having a lot of missing, we do command in Mplus that if you have your data by measurement occasion, it will do that. So anyway, we're going to look at 2 cohorts, 1961 and 1962. And they measured the frequency of heavy drinking in the years 83, 84, 88, and 89. So the measurement occasions are 83, 84, 88, and 89. And but what we're really interested in is how the development of heavy drinking goes across chronological age. So here's what the data look like. In 1983, we had the 1961 is the older cohort, and 1962 is the younger. So in 83, they were 22. The older cohort was age 22, and the younger cohort age 21. So the difference between the measurement year and the birth year. In 1984, we had the older cohort 23. In 1988, they were 27, and in 1989, they were 28. And likewise, for the younger cohort in 84, they were 22, 88, 26, 89, 27. Now, if we look here, we see that the age 22 is measured twice, age 21 only once, 23 only once, 27 was measured by, or is, I should rather say, age 22 is represented in both of the cohorts, as is age 27. The other ages are only represented in one cohort. Now, if you instead use age as this x-axis, then the ages 21, 22 through 28, then we can say which cohort provides information. So we know that in 1983, the older cohort had information on age 22, and in 1984, the younger cohort had information on age 22. For age 21, we only got information from the younger cohort in 1983. So that's how this was this particular box was created. So what we're interested in growth. Well, there are two issues here. There's whether the cohorts actually come from the same population, and as Bengt mentioned, that can be tested. We can test across the 2 groups to see if the structural parameters and the measurement parameters are the same for situations where the measurement parameters are represented in more than one group. And if they aren't the same, then this approach would not be appropriate, and the long approach wouldn't be either, because we'd be mixing people from different populations. So this builds on the premise that the birth cohorts come from the same population. Okay. All right, so on the right screen here, I'm showing how you would go from the bottom of the left screen to calculating time scores. So if we have ages 21 through 27, the time scores are 0, 1, 2, 3, 4, 5, 6, 7. And cohort, the younger cohort, 1961, or rather the older cohort, 1961, only has information on ages 22, 23, 27, and 28. So the only time scores that are relevant for them are the ones associated with those ages. So 22 is 1, 23 is 2, 27 is 6, and 28 is 7. So the only part of the growth model that they're going to contribute to are those parts. And likewise for 1962, the younger cohort, they only provide information for ages 21, 22, 26, and 27. So their time scores are 0, which is 21, 1, which is 22, 5, which is 26, and 6, which is 27. So when we're setting up the input, they will contribute only to certain parts of the growth model. Now, we can test the degree of measurement in structural invariance. So structural invariance is related to the structural parameters of the growth factor means, variances, and covariances. And we estimate the model with them free, and then we estimate the model with them held equal, and we can do either chi-square or log linear or log likelihood difference test to see whether or not the two groups come from the same population. And we can also test that residual variances of shared ages, of ages that have the same parameter held equal across the cohorts, how that works. So we're going to look at that in more detail, so don't worry. Actually, I think I'll put this one over on this screen. All right, so here is how we would go from this information to the input. So you can see that we have a grouping variable, which I don't think we've seen before in topics 3 and 4. So the grouping option names the variable in the data set that contains information about grouping, in this situation cohort. And cohort takes on the values of 61 and 62 in the data set, and we're going to give a label. So we're saying that we're going to use the label older for 61 and younger for 62. And in the model command, you can see that we have our growth model, IS bar, and then heavy drinking, 83 at 0, 84 at 1, 88 at 5, and 89 at 6. And that represents the time scores here for the younger cohort. So let me just say something about multiple group modeling so that this will make sense. In multiple group modeling in Mplus, we have an overall model command and a group-specific model command. I'm just going to go forward to show you that. So here, group-specific, we use the labels from the grouping option, model older and model younger. So we have in multiple group analysis the overall model command and the model older and the model younger, which we refer to as group-specific. You set up the full model in the overall model command. And the way Mplus works is then anything that's different for a particular group is specified in the group-specific parts of the model command. So here I'm giving the time scores for the group, and then in a group-specific model command for the older group, I'm going to give their time scores. So you don't, and if you're doing a multiple group model and the analysis is identical for all groups, it's unnecessary to even use the group-specific model commands. So you don't have to repeat everything over and over. Sometimes I'll get an input and it's, they have, for every group they say the same thing, and that's not necessary. You only should say for each group in the group-specific what's different. All right, so in the overall, we're talking about the cohort that ends in 6, which is the younger. Now, what do we have here? In brackets, the I refers to the intercept growth factor. The S refers to the slope growth factor mean in brackets. So the I mean, the S mean are in brackets. I and S not in brackets refer to the intercept growth factor variance and the slope growth factor variance. I with S refers to the covariance between the intercept and slope growth factors. Now, what about the numbers in parentheses? Well, whenever you have a number in parentheses in multiple group analysis following a parameter, that parameter is held equal across all of the groups. So we refer to this as an equality constraint, an equality label. So the means of I are going to be held equal across the groups. The means of S are going to be held equal across the groups. The variances of I and S and the covariances. All of these structural parameters are going to be held equal across groups. And I think I'll put this slide over here now, so you can see the full input. Whoops. Thanks. Please. Oh, okay. He follows the whole family with a camera constantly. Oh, okay. Just take a deep breath. All right. So now here on the right screen is the model older. So this is the group-specific model command for the older cohort. And you can see that we have the growth model for time scores 1, 2, 6, and 7, because those are the only occasions or years for which they provide information. So we're doing a growth model over years. And for model younger, and then, okay, and, oh, I have to go back. It's so complicated to show this. With only 2 screens, I need 8 screens for this. All right, so which one do I want? Okay, so now we have on this screen equality constraints for the heavy drinking variables. And those come about because of this situation here where in the age 22 is represented twice, both for 83 and 84. So, so this 83 with a 6 and 84 with a 6, that's holding those residual variances equal. And those are measuring parameters. So we're holding those equal. And then we have another situation where 88 and 89 are both cohorts are providing information for 88 and 89. So then we have 88, 89 with a 7. So those equalities, you must constrain anything like that to be equal. So any time we get information from more than one cohort, those parameters have to be held equal when the model is estimated. And, as Ben said earlier, they should be tested whether or not they're equal. And in the heavy drinking paper that I mentioned yesterday where we had dropout as a covariate, that was also a multiple cohort paper. And was where we got that staircase picture where we developed using that. So you can look at that paper if you're interested in this and see how we tested to make sure that all the cohorts were from the same population. Okay, so now just to remind ourselves, each cohort's getting 4 time scores, but the growth model for which we're estimating an intercept and slope growth factors actually goes over the ages 21 to 28. So this, even though we're doing it multiple group and there's 4 measurement occasions, the way that we're setting up the model is going to give us intercept and slope growth factors that go over several ages. All right, so let's see what we got. Well, when we have multiple group analysis, you get a chi-square contribution for each group. We got a chi-square, a p-value 0. And down at the bottom, we have fairly decent looking CFI and TLIs. And this is maximum likelihood, but it's a maximum likelihood in a situation where you can get chi-square. So you also get a log likelihood, and you get your various BIC and AIC. Your RMSEA also looks fine, as does SRMR. Now, although I'm showing you the third step in the analysis that Bengt referred to earlier, you should first analyze each cohort separately to even see if the same model fits. Because if the same model didn't fit in each cohort, it would really not make sense to put them together. And then as the next step, you would do the cohorts together with all parameters free, and then you would do what we're doing to test whether the cohorts come from the same population, and then if they do, then estimate the growth model. Okay, so here we have group older, and let me put group younger over here, 63. And group younger. Now, we can see the equality constraint. I'll just come over here since I'm here. And 83 and 80, well, we don't see the equality constraint on the residual variances. Why don't we see that? Did we? Oh, I'm sorry. Well, no. Oh, okay. Thank you. Okay, so here's our equality constraints for the younger and older cohorts on those 4 residual variances. And we don't have to show the equality constraints for the variances across groups, or we don't show them. But these, the means and the variances and the covariance up here, they were also held equal across groups. And this is what we're interested in. And like Bengt said, the mean of I isn't necessarily very interesting, but we are interested in the slope, mean of the slope growth factor, which is negative. And we're looking at heavy drinking over ages. The ages, let me remind myself, 21 to 28. So that would indicate a decrease in heavy drinking across ages. And then we were interested in the variances, both of the intercept growth factor and the slope growth factor. And we can see that both are large compared to their standard errors, and which would indicate that there was a lot of variability. The I variance indicates a lot of variability in heavy drinking starting at age 21, and variability also in the growth. So the growth being negative, but there was variability in that growth. And the covariance between the two is also negative, so those who, oh no, not the negative again. No, I'm not going to go there. No. Okay. That can be a question. And then I think we're going to go on to preventive interventions. So, but just to summarize, so when you have multiple cohort data, which you are using because you want to accelerate the collection of your data, and you can do 3 different things. You can, you can either spread the data out from measurement occasion to age, and then, like Bengt showed you the picture, you have lots of missing data, and that can be problematic as far as estimating the model. Or you can go to the multiple group approach like I just showed you. And the results between the multiple group approach and spreading the data out will be identical. You will get the identical results because they're exactly the same. They're just set up differently. And then the third is the @ option, which Bengt mentioned to you, which also should get the same results. Okay.
May I take your picture? Okay, I got signed consent from 200 people, except there are, maybe here I can see it, measure it. Okay. Smile. Perfect. So you can tell I'm on a short leash.
Oh, yeah.
Not.
The king.
So let's jazz it up a little bit and talk about this slide. And I was hoping that we would get visited by the person who inspired this slide. It is having to do with developmental epi. You want to say epi because otherwise your tongue gets twisted here. Epidemiological. So anyway, I was part of this prevention science. I am part of the prevention science methodology group led by a certain Hendrix Brown at University of Miami, formerly at Tampa. And it's originated here at Hopkins. They've been NIMH and NIDA funded for over 15 years. And anyway, we used to travel around to different interventions centers in mental health. And I'm a statistician, so I sat there and listened to the preventive interventionists' flowery language, trying to figure out what these psychologists, psychiatrists were talking about and trying to figure out how to translate it into statistical terms. So it led me to this slide here to just keep the memory of that. And they're interested in, as it says in the first bullet, they're interested in determining the levels and variation in risk and protective factors as well as developmental paths within a defined population in the absence of intervention. So I thought to myself, that must mean they're interested in developmental path is growth model, absence of intervention, well, that's the control group, that's the normative development, and levels and variation in risk and protective factors, well, that's time invariant covariates. Okay? Maybe approximately right. So that is a growth model with time invariant covariates for the control group. Now, what's this? Second bullet, directing interventions at these risk and protective factors in an effort to change the developmental trajectories in a defined population. Epi people always talk about defined population. And they're right in doing so, I guess. But what does that mean? Well, changing developmental trajectory seems to mean that the intervention, the Tx variable, should influence S. So that would say that you would do a joint analysis of the treatment and control group. Although now when I read this, it seems like it's saying more. You direct intervention at risk and protective factors. If they were covariates in the first model, then we're saying that Tx should influence the covariates and perhaps developmental trajectories, but could also influence the developmental trajectories indirectly through the risk and protective covariates. I'm not quite sure. I haven't seen them do that, but that's like putting a path model, so to speak, upstream, so to speak. That is, instead of just having covariates, not modeled, you can say that Tx influences covariates, which influences the growth process. So it's a more elaborate model on the covariate side. That's what I mean by upstream. And then finally, evaluating variation in intervention impact across risk levels and contexts on proximal and distal outcomes, thereby empirically testing the developmental model. Nice language, huh? Out of this, you get a very vivid visual vocabulary. You have then intervention impact across risk levels and contexts. All right. I interpret this to mean that the intervention can be differentially beneficial for individuals with different background characteristics and perhaps different baseline values. And we're going to take a particular intensive look at treatment baseline interactions. But what about proximal and distal? Well, I took that to mean that proximal is the outcome of primary interest. So that's the Y of the growth model, the Ys of the growth model. And distal I hadn't heard about until I got into this group, but that is some outcome that happens later. So you can imagine a growth model for math achievement from grades 7 through 10, and the distal could be high school dropping out or not. And now we're going to bring that together in one model. So that's what they wanted to do. So we went off and tried to do that statistically and develop a machinery that you will look at now. And then, 5 years later, you come back and show them what you've done, upon which they typically say, that's not what I meant. But, still you have a methods paper then, so that's fine. So talking about a paper here, my former postdoc, Pat Curran, and I wrote the 1997 psychological methods paper. And it happens here in Baltimore. That is, the data came from Baltimore, this prevention center, school-based preventive intervention, randomized trial. Many of you in the room are intimately familiar with this. Starting in grade 1, a good behavior game, a classroom-based behavior management strategy, promoting or reducing aggressive, disruptive behavior in these children in school, and aimed at longer-term impact on aggression through middle school. So you randomly assign this treatment, actually on the classroom level, which is interesting. So it's a multi-level feature embedded here, but we're going to ignore that for today. But the primary interest was this, what we're going to refer to as TOCA, a measurement instrument with several items having to do with child's aggressive, disruptive behavior like breaking rules, harming property, fighting in the classroom. And we're looking at grades 1 through 6. Some grades we're going to measure both fall and spring. Some grades we're only going to measure in the spring. And the question is if the good behavior game reduces the slope of the aggression trajectory across time, and whether or not, and this is a key interest, the intervention varies in impact for children who started out as high aggressive versus low aggressive. So the treatment baseline interaction idea. And here we have a fairly small sample size. You have 75 boys in the treatment group and 111 boys in the control group. And there's a series of analysis carried out in this paper from Psychological Methods. By the way, that's a journal that you may, if you're interested, if you're a substantive researcher, but are interested in methodology, that is a good journal where people, Psychological Methods really tries to force the writers to be understandable, force the description of the techniques to be penetrable, and I don't know to which extent we succeeded, but anyway, it is a paper that goes through 6 steps of analysis. It analyzes the control group analysis, so that's the development in the absence of intervention, the normative growth, in what does aggressive disruptive behavior look like among children in these classrooms. And then a separate treatment group analysis to see how similar they are. And then a joint 2-group analysis. First a simple model, and then a more elaborate model with the interactions. When I say interactions, I mean treatment baseline interaction. And then scrutinizing the final model using the sensitivity analysis by modifying some aspects of the model to see if the key findings are still there. And then step 6, do a power analysis to see, in this case you could ask yourself the question, the significant effect that we found, could we have gotten away with a smaller sample size to find it? Or if you didn't find it, what size of the sample should we have used to be able to find an effect estimate of that size? Here we go straight to the final result. And then we're going to work our way backwards to seeing how we did it. So this is, on the x-axis, you have the different time points. 1, 2, 3, 4, 5, 6, 7, 8, I think it is. And it corresponds to fall and spring of grade 1, fall and spring of grade 2, and then spring, 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 up to grade 6, or was it 7? 6, I guess. And on the y-axis is the TOCA. So the higher the score, the more aggressive, disruptive the child was. Now the three pairs I'm just dividing it into three for the purpose of describing the results. There is no such grouping in the analysis. But if you look at, for instance, the top pair, what you're looking at is the control group development. That's the normative development versus the intervention group development. So the intervention seems to reduce the disruptive aggressive behavior over time relative to the control group. So this is normative development. This is what the intervention does. They start out the same because the first time point is the pre-intervention outcome, where the intervention hasn't started. That was the first measure in fall first grade. Then you see a big effect for those who started high, a smaller effect for those who started medium. There's still an effect, but we don't know if it's really significant. And then for those who started low, it looks like a so-called iatrogenic, I knew I couldn't say that, iatrogenic effect. That is a negative effect if you are to believe that this is significant. That is, the control group does worse than the treatment group. So we don't know if that's truly there or not. So this is the way, this is an analysis then that answers the question that many interventionists ask: for whom is the intervention beneficial? For whom? We often find that interventions are not beneficial for everyone. That is, the so-called main effect of the intervention is not significant. But we find that it's significant for subgroups of individuals. Now, you could subset individuals here. You could capture the three different groups by splitting it three ways. The pre-score, the pre-test, the baseline value can be, baseline variable can be divided into three equal parts, for instance, and then you can do an analysis in each of the three parts. But that's not a good strategy because you really reduce the power by cutting the sample size in third. Excuse me. This analysis is a joint analysis of everyone. And the finding of for whom it's effective, the intervention is effective, is done in the modeling. That's one interesting aspect of this analysis. We'll come to a couple of others as well. So here, on the left screen is how it was done, how we got to the picture on the right. And it is a two-group analysis. You have the control group at the top and the treatment group at the bottom. And you have, I guess it was 8 measurement occasions. And this is really the magnitude of number of time points that you want to have. If you have a fairly elaborate development like this, a quadratic, say, you want to have a good amount of time points to explore the developmental curve. So although we say that 4, you really should have 4, not 3, we don't mean that you should be satisfied with 4. You should push for more. And of course, that's related to what the development looks like. If it has a lot of ups and downs, for instance, like that cubic loneliness of twins, And then you may need quite a few. In any case, so you have a quadratic growth model for the control group. And the way it's drawn, it looks like I and S are correlated, but there's no correlation with Q, which must mean that the variance for Q is fixed at 0, which happens very often in practice, as far as in my experience, that you don't need Q to be random, only I and S to be random. So you can say Q at 0, Q at 0. And since it has no variance, it certainly has no covariance with the other two. And then another feature is that we use P with. We have pairwise correlated residuals here. I don't know to which extent that was really needed. And then we have the treatment group, and it is a model for the same variables. And we are going to have some things the same as the control group and some things different. So these 3 growth factors here are going to be having the same parameters as these. So we're going to, within the treatment group, we're going to argue that if there had been no intervention, this is how they would have grown, based on I, S, and Q. So we hold all of the parameters equal between the 2 groups for these. But we're going to say that the treatment group has a treatment-specific value added, which is getting more popular now in education, value added feature. It's going to be another growth factor. In this case, a linear growth factor, as it turns out to be. These are 1s here, the time scores. So this is the extra development beyond the normative that is due to the treatment. Note that we don't have a treatment control dummy variable here. This is the multiple group approach. The treatment control distinction is handled by the 2 groups. So here, once we are in this framework, we can now pinpoint the modeling to better capture the question, is there a treatment baseline interaction? And we're going to define baseline not as Y1. We're not going to pay the price of moving Y1 down as a covariate. I would argue strongly against that approach. Y1 is one outcome in a time series, in a growth model, just like for the control group. But what if you need a baseline to relate to? Well, you have a baseline. I is the baseline. I is a much better baseline than Y1. I, defined as initial status, is the pre-intervention status, the systematic part of the variation in Y1, purged of the time-specific and measurement error variation, which sits in the residual of Y1. Now, we just have to get FDA on board on that. But it is a latent variable definition of baseline. And it says that then you can model the treatment baseline interaction by letting I, the value of I, influence the value of the treatment-specific development. So this treatment-specific growth factor T can be regressed on I. So for instance, when I is high, you may have a specifically beneficial treatment effect. So that is what we've used up here. I goes from low to high, and the treatment effect increases. So this arrow from I to T says that if it's significant, if that arrow is significant, has a significant slope, then you have a treatment baseline interaction. And with baseline defined as a latent variable. This has been used, and people have published on that, and it's quite doable. How do you set it up in Mplus? And I would say that this is a better way of using multiple group analysis. The alternative would be to have the same growth factors in the 2 groups, get rid of this, and just test if the S and Q means are different between the 2 groups. That's a less powerful analysis than this, and it also cannot capture the treatment baseline interaction, cannot capture the I to T. So look at the right here now. You have the control group as group 1 and TX group as group 2. We have then a model that's specified in the overall, and then on the next slide, 71, I believe we have the group-specific model. So we have an overall model that's true for both groups, and then we modify it slightly for one of the two groups. That's the thinking here. So on the right, then, you have the growth model I, S, and Q with proper time steps, time scores. Although here, with the quadratic, I would not go up to 11 here anymore. I would divide those time scores by 10. And then you have another growth model, I and T, which corresponds to the T here and the I, which is linear. Only linear. You could say that the treatment-specific effect is linear or quadratic, depending on the data. And you switch to the alternative growth model parameterization that we also used yesterday when we talked about latent variable interactions. So instead of having intercepts fixed at 0, we hold them equal, and thereby we cannot also estimate the mean of I, but fix it to 0. The equality. And then we talked about the variances and covariances and means of the growth factors here. And the parenthetical statements, 1, 2, 3, 4, 5, 6, imply that, that those parameters are held equal across the groups. So when you have something in parentheses like this in the overall model, the overall being for both groups, it implies that those parameters are held equal across groups. We then have in the overall model T on I, bottom of slide 70, that's T on I. And we modify in the control group by saying T on I at 0 and T at 0. So in the control group, we have no T. In the control group, we have no T. You don't have any T factor here, so we get rid of it by saying that its mean is 0. Its variance is already fixed at 0, residual variance is fixed at 0 on the previous slide. So we only had to fix the mean at 0, and the slope T on I is 0, getting rid of T in the control group. I think that these two statements I don't think are necessary. But they just emphasize that those parameters are the same in the control group. But I think that's already by default the case by mentioning those equalities in the overall part of the model on slide 70, and Linda agrees. So you get this model, and lo and behold, you get a non-zero p-value. And it's a reminder that you're much more likely to get well-fitting models in terms of p-values if you use small samples. Always use small samples. No, just be aware of that. It's just a power matter. You have less power with a small sample to reject the model that's false. Another way to get really well-fitting models, folks, is to choose variables that have very low correlation, because then also you have very low power to reject the model. Small samples, low correlations, and you have great fit. I didn't say that. And in the control group, then, you have T on I, non-existent, so it's zeroed out here. But in the treatment group, slide 76, you have T on I, significant negative, meaning that the development is pulled down. They have a lower slope of the aggressive disruptive behavior in the treatment group. Significantly lower development, as we saw in the graphs. You find that in the treatment group. And that significance then is a significant treatment baseline interaction. Note that the mean of t, or the intercept of t on slide 77, is insignificant. In the absence of that slope, this would be the main effect. The main effect. If you analyze this model on the left without I pointing to t, you would only estimate the mean here. And that mean, which is corresponds to the intercept here, is insignificant. So in these data, there was not a significant main effect of the intervention, but we were able to pull out a significant treatment baseline interaction effect of the kind that those who are initially more aggressive benefit significantly from the treatment, in line with this picture. So these pulling down of the curves in the intervention group corresponds to this. So these plots are created from these estimates on the right. So that made the investigators happy. So you can read about that article in Psych Methods 1997. So that's an illustration of the specific multiple group modeling you can do when you have a randomized intervention. And with that, we take a deep breath and ask ourselves, how are we doing on time? We have thumbs up from Linda, the parliamentarian. We're doing fine. So take a deep breath and stretch a little bit, because now we're getting into even deeper waters. Yeah. Maybe you should have a little aerobic hand-raising activities again. All right. Multiple indicators. What are they, and how can you deal with them? So we moved quite far down on our list here, folks. And here is a model then of this kind. So once again, these two slides say the same thing. Which one do you prefer? Where are the biostatisticians in the group? Yeah, that, of course, yeah. But let me start here then, so I can follow it. So you have, in this case, you have 3 time points. Time point 1, time point 2, time point 3. At each time point, you have 3 indicators. I know it's not pedagogical, but you can tell. T1, T2, T3. Each time point, you have 3 indicators of a latent variable. Latent variable, you may call it F1, F2, F3. You can fill in the circles if you like. It's okay. And you have then this is a single factor model. You've probably done a very careful factor analysis first and found that for these 3 items, 1 factor is great. You probably have a much bigger set of items from which you've chosen these 3 as good representative of this factor. Because you know that with only 3 items, you cannot even reject a 1-factor model because it's just identified. So the idea is that we have the same items, same set of 3 items measured at 3 different time points. And we have continuous outcomes here, and therefore we're going to talk in terms of intercepts and slopes in a regular linear factor analysis model. At the very bottom, we have the growth model aspect. You have an intercept and a slope growth factor. And in this case, the growth is with respect to the latent variable constructs, F1, F2, F3. What should we think about here in this modeling? We should think about the fact that we want to make sure that F1, F2, and F3 represent the same construct over time, measured in the same metric, on the same scale. That's the key thing in growth modeling, that the dependent variable of the growth model needs to be on the same scale across time. You can't take a variable and standardize it at each time point and then expect to have a meaningful growth model on it, because you're not on the same... You've gotten rid of the scale that's natural. And you can't change the variable across time, because you can't study change in an individual when you're changing the outcome. We'll get to that a little bit later. So you would want to have measurement invariance across time. So the intercepts are called nu1, nu2, nu3. Slopes are called lambda. You want the nus and the lambdas to be the same across time. Measurement invariance. Now, we're not going to need all of the parameters in this model. So, for instance, you see that you have zeros here. 0, 0, 0. Those zeros are the intercepts in the regression of f on the growth factors. The intercepts in the regression of f on the growth factors are not needed in a model, but can be fixed at 0. It's almost like, the fixed 0 intercept for an observed y. So then the observed means, how they vary across, it's instructed to consider that, how the observed means change over time. So let's take the mean of the first item here. You have 3 items. Item 1, I claim that the observed mean, the mean for that first observed variable is nu1, nu1 being the intercept. And that's because the mean of the intercept growth factor is 0 here. We're going to use parameterization 2. Linda said that parameterization 2 is used when we have categorical and multiple indicator models. So the intercept mean is 0. And the intercept of the factor, the f1 construct, is 0, which implies that the mean of the factor is 0 at the first time point. We do that sort of setting a reference value of 0 for that factor mean, which can then change over time. So the mean of this is 0, which implies that the mean of the observed variable is nu1. Nu1 plus lambda times 0, which is nu1. And the mean for the second item is nu2, third item nu3. At the second time point, the mean of the first item is nu1 plus alpha 2, where alpha 2 is, in this case, the mean of the slope growth factor. So that the mean of f2 is 0 plus alpha 2. So alpha 2, so the mean of this is nu plus lambda times alpha 2. And for the second item, it's lambda 2 times alpha 2, and lambda 3 times alpha 2. And with linear growth time scores 2 here, you'll have nu1 plus 2 times alpha 2, nu2 plus 2 times alpha 2 times, lambda 2 times alpha 2, etc. What you have at the top then is what you would expect, how you expect the means to change over time. So if you plot the means, they should go for the first variable from nu1 to nu1 plus alpha 2 to nu1 plus 2 alpha 2, so linearly. And for the second item, from nu2 to nu2 plus alpha, lambda 2 times alpha 2, so to 2 times that. So the second item may not have as steep of a slope or a steeper slope, depending on lambda in its growth over time than this. Lambda 2 may be smaller than 1, so then item 1 is here, and item 2 is a little lower. But the degree of lower should be equal to the relationship should be equal to the lambda 2 size. So there are certain things that have to work out. The change over time in the means has to correspond to the sizes of the factor loadings. Otherwise, the model is not correct. So Linda's going to go through examples and test this to see how that works out. And I think she begins on slide 82.
I think so. Okay, so we're going to take a look at a multiple indicator growth model in practice. And let's start over here. Okay, now when you decide that you're going to do one of these multiple indicator growth models, as Bengt mentioned, it's really important that you carefully test for measurement invariance across time for the latent variable that you're interested in developing a growth model for. And that should start out actually, and this builds on, we're going to be discussing measurement invariance across time, but this builds on the topic 1 measurement invariance across groups for continuous outcomes, which we went into in detail the last time that we were here. So for each time point, so you start out looking at your data for each time point. You would start out with an exploratory factor analysis just simply to answer the question, at each time point, do we have the same number of factors? So we're, at that point, with the exploratory factor analysis, we're only concerned with whether or not the same number of factors are found at each time point. So at a very minimum, we should have the same number. They should meet that. If they all have 1, then the next question is, do they mean the same thing? And you also want to determine the shape of the growth curve for each indicator and for the sum of the indicators. I think this was alluded to a little bit yesterday, but it doesn't really make sense if the growth curves are not similar for each indicator to put them together in the same factor. So you want to do, at each time point for each indicator, find out what kind of a growth curve shape they have. So it's the shape that's the concern, not the exact values, but just the shape. So do they all have a linear shape? Are they all quadratic? Or how do they look? And then you can also check that by summing the indicators. And then you can fit a growth model for each indicator, which I already said. Then you want to do a confirmatory factor analysis of all time points together. And you want to do that in 3 steps. So let's say you had 3 factors, like Bengt showed on the picture. Then at each time point, or you want it to do the confirmatory factor analysis. Let's say you have 3 time points, 3 factors with 9 factors in different ways. 1, without measurement parameter invariance. So the first time you analyze it, you want all of the measurement parameters, the intercepts, and the factor loadings to be free across time. So this is the first model. Then you can run it holding the factor loadings equal to test factor loading invariance. And this is just the same steps we did in topic 1 with multiple group analysis. Then in the third step, if you determine you have invariant factor loadings, then you can also hold the intercepts equal across time. If you establish that you have measurement invariance across time, and that in fact the latent variables at all the time points actually represent the same thing, then you can do the growth model with the measurement invariance in place. So once you establish measurement invariance, you hold those parameters equal in the next parts of the analysis. So this is what you would do. And then you might ask yourself, why in the heck would I want to do that? That sounds like a lot of work. But there are some advantages of actually using multiple indicators instead of just averaging the indicators and doing the growth model on the average score. One is that the weight, when you average, you're assuming equal weights for each item. When you do factor analysis, the factor loadings are unequal, and therefore you have unequal weights. Another thing is that when you are testing for measurement invariance across time, it is possible that you will find that you actually have partial measurement invariance. And without keeping the multiple indicators, you would not be able to specify that you have partial measurement invariance. If you sum the items and take the average, you've built the fact that you have measurement invariance into averaging those items. So then you have no confound. You also can separate time-specific variance and measurement error invariance, and it's a more powerful model because you have smaller standard errors. So you have more power to detect differences from zero. So what we're going to look at here is classroom regression data, but the same data that Bengt talked about in his treatment control study. So the data, TOCA data from the Baltimore Public Schools, the research carried out by Johns Hopkins. We're going to look at 4 time points, so spring grade 1, spring grade 2, spring grade 3, and spring grade 4. And we're going to have 7 aggression items in our latent variable, which we're going to call aggression. Breaking rules, fighting, harming others, lying, being stubborn, teasing classmates, and yelling at others. Okay. And this is a path diagram of the model. We're only showing 3 measurement occasions. The ... here is the third one. So it's 1, 2, ... 4. And then at the top, we have our 7 items, which we're only showing for 2 of the factors, the residuals, arrows here. And we're going to estimate a linear model. We have 2 growth factors, the intercept growth factor and the slope growth factor called I and S. So I'll move over here for the input. So we're starting at the point where we're just going to be looking across time, at the model with no measurement invariance. So here we have F12A, 22A, 32A, and 42A for the 4 time points, the 1, 2, 3, 4. And we have the items also measured across time, BRU 12 through yells at others 12, and the same thing for these. So we don't have any equality labels, so nothing is held equal across time. So that's the first model that we want to look at. And what I'm going to do here is I'm going to show you all the models, and after I've shown you the models, then we're going to look at the chi-square difference testing of the models. So then the next thing is what I mentioned, that we want to have factor loading invariance. And so we do this by putting equality labels in parentheses to indicate that. Now, if you note that the first factor loading is always fixed to 1 to set the metric of the factor. So breaking rules here, that factor loading is fixed at 1 across all time points. That sets the metric of the factor. Now, for the other items, the 1-6 in parentheses, the 1 applies to the first item, the 2 to the second, and then we have 1 through 6 across time. So we're holding those 6 factor loadings equal across time. And just a note, when you use the list function, the dash here for the labels, you also must have a list for the parameters. So you couldn't have the parameters listed, the 6 parameters listed, and then put 1 through 6 in parentheses. That wouldn't work. So this is factor loading invariance. And then we move from factor loading invariance to also holding the intercepts invariant, which I guess this is identical. So I will.
Next slide.
So I can just use this one, right?
Yeah.
Right. Okay. So anyway, so this is the first part, factor loading invariance, and here's the intercept invariance. And we refer to the intercepts in square brackets. So here's Brake's rules at the first time point, the second time point, the third time point, and the fourth time point. So I'm holding the intercepts of breaking rules equal across time by putting that 7 in parentheses. Same thing for stubborn. I put 11 in parentheses. That's going to hold those intercepts equal. And this is the second possible growth model parameterization that we talked about, where we have the equality of the intercepts over time. Now we have to have, when we need to have the factor mean 0 at one time point and free at the others. It has to be 0 at one time point for model identification. So this is the model where we can test both factor loading invariance and intercept invariance. Okay, and then we have also the model where we have, I'm just going to focus on the intercepts because you can have partial measurement invariance, and I'm showing an example of going from here and finding out, and we're going to look at the results last, that the intercepts were not invariant and how we can change that. So we saw there was an issue with hitting others, so we've removed the fourth time point hitting others, which means it will no longer be held equal to the others. It will get a different estimate. And the same thing for stubborn. We've freed 2 of them. And teasing classmates. We've freed 1 of those. So this is an example of partial measurement invariance, where some of the parameter, we'll see that model fit was worsened when we had total measurement invariance. And so we wanted to have partial invariance to see if we could lessen the worsening of fit. So I think I'm going to put that over here since it goes down so far so everyone can see better. Okay, so just to summarize what we did, we went through a series of models for testing measurement invariance across time. All parameters free, factor loadings equal across time, intercepts and factor loadings equal across time, some intercepts not held equal across time, representing partial measurement invariance. Now, topic 1 goes through all of these things in a lot more detail than we can do today. So now we have the models listed on the left, chi-square difference, and if it worsens fit, it's indicated by an asterisk. So with non-invariance, we have with nothing held equal, measurement non-invariance, 566.08 is the chi-square with 344 degrees of freedom. When we hold the factor loadings equal, chi-square goes up, but it does not go up enough to worsen model fit. So that would tell us that we do have factor loading invariance. There's not a problem. Now when we impose also intercept invariance, the chi-square value goes up to 654.59, and that's a chi-square difference of 73.30, which does worsen fit. So we know that somewhere we have some problems with the intercepts not being invariant. And we can look at modification indices to see that. Then we could estimate a model, and we wouldn't do all of this stuff all at the same time. We wouldn't add all those intercepts after looking at modification indices. But here we show the final result, factor loading and partial intercept invariance partial factor loading and partial intercept invariance here. So it only went up to 606, not to 654. This still worsens model fit, but we decided at this point that that was as far as we were going to go in this exercise. You might not want to make that decision in your own research, but anyway. So we're going with this model. And just another note, if you have measurement non-invariance and you model it, then that's okay. So as long as you recognize it and you allow it to be modeled, then you can go on with those coefficients. The issue is how much partial measurement invariance can you have? How many parameters can you have that aren't invariant and still assume that the construct is the same? And then we have factor loading and partial intercept invariance with the linear growth model put on, and that does not worsen model fit. And we have a description here, which we really don't have time to go through, but it's just telling you the difference in degrees of freedom and where it comes from. And finally, let me just show you the growth model. So we want to put the growth model here. So we have the first factor with time score 0, then 1, 2, 3. And in the alternative language, you see what's done behind the scenes, which you want to know. And that's that the factor mean, which are now intercepts in the growth model. So the factor intercepts are fixed at 0, just like the observed variable intercepts are fixed at 0 in the growth model. And since we have the equality parameterization, the mean of I is at 0 and S is free. And we don't have time, so we won't go through the oh, well, maybe we should go through. Yeah, we'll talk about this, which actually shows the results. But so then here, this is the item stubborn on the y-axis, and this is the aggression factor on the x-axis. And let's take a look at one value on the aggression factor and look at what it says about earlier and later grades as far as the item functioning. So if you have a value here on F, aggression, you go up for earlier grades, the value on stubborn is lower, and for later grades, it's higher. And this is the measurement non-invariance. It's differential item functioning. The item behaves differently for earlier grades than later grades. And you really don't want that. I mean, so that you would want that item to behave well for all grades. And then you also have a distortion of how the factor is interpreted. If you go in up on the y-axis at a particular value of the item stubborn, in later grades, you get a lower factor score than in earlier grades. So it distorts, when an item is non-invariant, it distorts the factor meaning also. Okay, so anyway, now we'll take questions. I think so. It's too late.
All right, so time for questions.
Banked. I took that.
Yes. Slide 59.
So there, the residuals were held equal.
I'm sorry.
Yeah, the residual variances are held equal across the cohorts because those individuals are of the same age.
So they provided information about the same age. Well, maybe we should go back.
I think it was age 22, right?
There. So 83 and 84 both gave information about 22. And likewise, 88 and 89 provided information about, or cohorts, two cohorts provided information about the...
age 22 information is provided by cohort 61 and 62, 83 and 84.
And I'm comparing that with the growth model with like multiple indicators.
Uh-huh.
Their like residuals were not equal. So
Right.
I'm not confused, but whether like.
So are you asking why the residual variances weren't held equal in the multiple indicator model?
I mean, I'm not confused, but it's like whether strictly variance or slowing variance.
Oh, okay. So which slide is that now? The multiple indicator? So now you have a different question about multiple indicators. That's on slide...
Maybe 89. they are like reuniversal or not as equal.
Yeah, okay, so let me interpret the question for those of you who don't hear it. So this gentleman is asking, why did we impose only invariance of nu and lambda across time and not of the residual variances, which is a stricter form of measurement invariance? And the answer is because that's not necessary. That's a very strong form of invariance, and it's not necessary to be able to do the growth modeling.
And in the multiple group, multiple cohort situation, you're specifying across cohorts. You're holding things equal where both cohorts provide information for the same parameter. So because both of those cohorts had information on age 22, they both provided information for that residual variance. And so we would want to hold it equal. We wouldn't want to estimate 2 residual variances. We only want to estimate 1.
This is under the assumption that you believe the cohorts are exactly the same. Now, of course, you can relax many of these assumptions. And so the question that you maybe implicitly are asking is, how many of these equality constraints can you relax in the multiple cohort and still talk about the same growth model across the cohorts? And yes, that's true. The residual variances being different across the cohorts is not a necessary one in that model either. In fact, when we did this analysis, there were very few cohort differences. The only cohort difference I found, I think, was with respect to the mean of a covariate. The mean of early start of regular drinking had changed over the cohorts, but everything else was pretty much invariant. Next question. Yes?
I have a general question, maybe some conceptual confusion. What's the added value that this multiple indicator growth modeling brings to the earlier analysis of the same data? It seems that they're answering different research questions.
Are you talking about the treatment control example?
Yeah, so slide 69 versus slide 80.
So you do.
I'll do 69.
Okay, I'll do 80. Oh, okay. Well, basically, they're different models. In here, we're doing a growth model on aggression, and and here we're looking at a treatment control situation where the research question there is, I guess, does the treatment have an effect? And here the question is, how does aggression develop over time?
And in this case, this is the total TOCA score, or the average. So maybe your implicit question is, what would we gain if we used the multiple indicator approach on the right and added that to this model on the left? Right. And the answer would be, you would get better results in the sense that you would be able to test, first of all, following Linda's principles, that there's the same number of factors across time. And the implicit summing up or averaging of the item says that you have one factor. That may not be absolutely true. Not only are you saying that's one factor, but you're saying that the factor loadings are essentially equal, and they're all across items and also equal across time. So all of those assumptions are probably not fulfilled fully here. So you probably would benefit from doing the factorial analysis and adding this feature to this model. So right. You could easily add this feature, multiple indicator feature, to the modeling idea on the left. It would just be more complex, but right. More correct and more fine-tuned results. Yes, gentleman in the middle.
One question about sticking with slide 69 is, say you didn't have a fully randomized experiment, but instead you had a quasi-experiment where you had a propensity score matches. Would you just add propensity scoring as a predictor of I to control for initial differences?
So the question here is, what if you didn't have a randomized study, but what if it was a quasi-experimental study? Quasi-experimental studies are now a popular technique to deal with those kinds of data is to use so-called propensity score analysis, where you estimate the propensity. Here your logistic regression knowledge comes into play. You estimate the probability of being chosen for treatment as opposed to not being chosen for treatment. And it may not be random at all, but you have a set of background variables that predict the probability of being chosen for treatment, and that is then a propensity. And then you divide individuals into, say, 5 different groups of propensities, and within each such propensity group, you do a treatment control group comparison. So the question is, how do we combine that kind of propensity score analysis thinking with this model? And again, I have no idea. But it would seem like you could, you have then a set of background variables that you do this logistic regression first step of the propensity score analysis, and you would have, I guess you would have a categorical background variable, a nominal background variable, which would be a multiple group analysis in a sense, I think. The propensity categories, do we have a propensity? Where's our propensity score?
Liz?
Why am I saying this? Liz, you should come up and tell.
Yeah.
I may be totally off the wall here. We have a propensity score, local propensity score expert right here, brought in for the occasion. Liz Stewart, combined biostat mental health professor.
She's not talking.
I don't have a quick, easy answer.
I think it's unexplored.
Yeah.
I think there is a potential for combining the two ideas somehow, but we don't have an easy answer right now. Thank you for not having an easy answer.
I'm losing my voice, so I can't.
Oh, okay, all right. Yes, you have an answer?
No, question of follow-up. If you're using propensity scores in a model that you might not be talking about right now, but shouldn't you call that account for degrees of freedom by having the benefit of all those scores? Would you include that as a degree of freedom penalty in a model?
Well, we don't know what
Maybe.
we do yet.
But I don't know is the truthful answer.
Why, I mean, wouldn't it be wise to consider penalizing yourself?
I don't even know how to bring them in, so but it's always wise to penalize yourself. Yeah, but you're probably right. Yes, in the background. Slide 69 and 70. Would you do
We have-
70?
Sure.
I was trying to figure out the T was kind of added smoke. You could have specified that in the syntax. You have that IT bar language. But if you're sharing an I, and I just, relative to yesterday when we had the C bar, I'm trying to understand why they're sharing the I here and how that gives an added slope rather than having distinct I and slope for this type of argument.
But
Yeah,
you really only get one eye.
That's what I'm asking about.
Yeah.
So the question is about this double I here.
I can say how it works behind the scenes. Well,
It's a second
if
day,
you
folks.
give the, but it's
Soon
the
we'll
sa-
start bickering.
Yeah.
No.
Anyway, when you use the same thing here, what I does is it fixes the factor loadings of I to 1. And if you say it again, it just fixes them to 1 again. So you still just have one I.
It does nothing essentially.
It doesn't do anything. But if you didn't put it down, if you only put one name, then Mplus would think this is an intercept-only model. So you wouldn't want to put a different name, like you wouldn't want to have I1 and I2. But if you have the same name, this is just, it doesn't do anything,
And like
except
Linda
make
says,
sure T is a slope.
If you only said T, Mplus would think it's a different intercept. So it's just a naming convention.
So are there paths from T to the indicator directly fixed at 1, or is it?
Yes. So yes. Well, no, exactly.
No.
Sorry. Maybe I think I misspoke when I said that. I think I said they were 1, but they
No,
are
it's
actually
0, 1. It's another
it's
slope
it's a
growth
linear. It's a linear growth. It's
But-
not the status change. It's the linear growth change.
I don't think you misspoke. I think you said it's linear, whereas up here it's linear and quadratic.
Thank you.
You're welcome. I have to give you something.
All right, it's your show. All right, we have a question here.
For a question about the multiple group and multiple cohort.
Okay.
58. Is it possible that you put different worksheets shape for different cohort?
So for you to have a model other, so is the question that you wonder whether you can have a model other than a linear growth model,
Right.
like a quadratic?
The younger one we just put linear, and then the older one we add quadratic to.
Well,
So
no,
this
because
person was a linear growth model for the younger and a quadratic growth model for the older.
but no, that wouldn't work because we're not estimating a separate growth model for older and younger in this situation. We're estimating a growth model from 21 to 28, from ages 21 to 28. But we have two different cohorts that bring us information about those ages. So we're really only estimating one growth model, not a different one for younger and older, the same one for everybody. But we could estimate a quadratic model for everybody, or a linear model for everybody, or a free time score model for everybody.
But if you really think that older and younger have different growth curve shapes, then you would do a separate analysis of them. You wouldn't do a joint analysis because they wouldn't have the same meaning of the growth factors. So it's not having the same growth shape is the same thing as having measurement non-invariance. And when you have measurement non-invariance, you don't want to compare the latent variable parameters because it's not the same latent variable. They don't have the same meaning. But it's perfectly okay to have different growth shapes for the different cohorts. You just wouldn't analyze them together.
Let's say that the data that you have is something like this, and then stay on the same topic, binge drinking drops, for example, after 25. I wouldn't know how to model that one with these kinds of data.
Oh, so binge drinking, usually goes up from the early 20s, peaks at 25 and goes down like this. So if you have a cohort that's older, you would say that you only have the linear downward part of it, whereas if you have a younger cohort, you have the going up and coming down. So is that what you're thinking about? Yeah. So, well, in that case, still though, they're all observations on the same quadratic shape. It's just that you're looking at different segments of the curve. So that's fine to stay with one growth model for that.
Can you do piecewise?
Yeah.
You can do piecewise too, but then you assume that you know where the peak is. Unless you do this change point analysis. But yes, in the back.
On the same slide, if you had a covariate in the model, would the output that you're getting in brackets for the intersection slope be the same mean that appears on the Tech4 output?
Yes, they would. So if you had a covariate, and therefore you were interested in the means instead of the intercepts of these growth factors, you would find them in Tech4, and they would be the same. No, the means would only be the same if also the regression coefficients of I and S on the X is the same. So the intercept and well, actually it wouldn't be the same because the means, that would also assume it would only be the same if also the sample means of the covariates were the same across the cohorts, which was what I found was not true for the early starting of drinking. But if all those three are equal, then Tech4 would show the same means across the groups. Yes?
To clarify, the defaults for testing for measurement variance across time are the same as the defaults when testing for measurement variance using multiple group analysis.
Yeah, so the question is, would we use, well, I think the question was, would we use the same defaults when testing multiple group invariance as testing across time invariance? We would use the same testing strategies, exactly.
Because on slide 86...
Okay, now she's going to prove me wrong.
Here, supposedly, this is not testing for measurement invariance.
Right.
But I know in the user's guide it says it's a default.
Yeah, okay.
Yeah,
so
no,
that's why I
so-
changed your word default to strategy in my
Okay.
answer.
So the
defaults are different, but the strategy is the same.
The models to test measurement invariance are the same, but because the defaults for multiple group analysis are for the intercepts and factor loadings to be held equal across groups, then the inputs aren't going to look the same. But the
Because,
models are going to be the same.
Because at this point, the program doesn't know that you have longitudinal data.
So there,
this could be different. This could be different variables. Totally.
So in this case, nothing is being held.
exactly. There's
Right.
nothing held. The only equalities are across groups
Okay.
by default, not ever across time.
But if you're going to do, so the first step of this multiple indicator modeling was what I would call longitudinal factor analysis. That is, you make sure that you have invariance of the factors across time. All right.
Okay, well, maybe it's time for lunch.
Time for lunch, and when do we have to be back?
We have to be back by 1:30.
1:30.